Okay. All right. So the main purpose I'm trying to have a session today is to give you a little bit sense of how to use MATLAB and how to do your project. This is not going to be a step-by-step guide for you to use MATLAB or do the project. It's just going to give you some kind of a general information because MATLAB is kind of so powerful and so complicated. It's almost impossible to kind of even read through the MATLAB help from the first page to last page. There's just so many contents in there. Firstly, before I continue, I wanted to get some, where's my Zoom interface? I want to just get some response from you guys. Anybody can hear me? Could you just say a word or something, or put a message?
Yeah, we can hear you. We can hear you.
Yeah, everything clear? Okay, you can see my screen.
Well, the only thing is that I didn't know that you started the session today from 8:30 this morning.
Okay. I put that on the kind of student forum. Let me share the screen. Okay, that might be. I thought everybody will get an email from, like, if I post a message over here, you will get an email, but obviously that's not the case. Maybe did anybody get an email from this? If I post a message over here? No?
I think normally what I would like, the notification that I received are from Sol's email instead of a forum.
Okay, I'm a bit lazy for that because I thought you can get a message, because I always get a message when somebody else is posting here. So I assume everybody will get a message, but that's okay. If you guys need further kind of consulting time, I can be available from 8:30 to 9:30 this time on Thursday morning. So instead of I'm going to be here all the time, could you please just send me an email if you need me? I'll be available. I'll be available normally like Monday consulting time, and from 9:30 to 10:30, I'll do some kind of extra lecture based on my understanding that the area you guys might need help, and based on the feedback you guys give to me. So feedback is important. Just make sure don't hesitate to raise your hand or just talk, okay? Because when I share the screen, I actually don't see all your kind of chat face and the participant list. I can, but it's kind of cover my screen. So I normally won't be able to see those things. So just start talking. I'm fine with that. Okay, so don't be shy or don't hesitate to disrupt me. Okay. Okay, so I'm going to give you some quick rundown. It's not going to be step-to-step guide because I assume you have some basic understanding of MATLAB and continuous time control theory, because I only have 1 hour. So just quick go through with kind of one example and some knowledge that related to that example. I will do a little bit explanation. Okay, so MATLAB. So I expect you guys be able to set up MATLAB on your computer. You can get help by clicking the help documentation. So I didn't install everything. I installed the control system toolbox and Simulink. Those are the two things we need. There's other things like Simulink control design. These are advanced tools, and you can use that, but it's not necessary. So the main part I wanted to you guys need to use is the control system toolbox, and you can also click that document PDF documentation. It actually brings you to the MATLAB website. So there's a bunch of documents here. I already put this user guide on Moodle, so you can flip through that. It's quite a daunting document. So you can see there's like 1,000 pages of this document. So I don't think it's a good idea you read from the first page to the last page, and you don't learn much by doing that. Right? The main reason is this document, like 1,400 page, 95% of this document, we don't even need to use it. Okay, there's so many advanced features, things that we don't need. Okay, so we're only doing the very basic things here. So I highlighted a few pages, so that's the information. And also you don't have to worry about this. I'm going to turn this into PowerPoint slides and get a copy for you guys afterwards. So you don't have to take any notes at the moment. So this is just some of the sessions that I think is very relevant to us, and you need to look at those sessions in the document. So this is coming from this document. So what I mean by 5/19 to 25 is if you look at each one on this page, it gives you this numbers. So this is 3.2. It's 5/19 is somewhere. Is that 5? Oh, that's 8 already. So it's somewhere here. Oh, that's 7. I can't remember exactly, but it's some of these pages that I think is very relevant to us. So it's 5, 7, 8, 11, and 12. So those added together, maybe 50 pages of document. I recommend you to read through. They are very kind of relevant to what we are trying to do. And also for control theory, there's many different ways of addressing one problem. Yeah, there's not always there's multiple methods you can use to solve one problem. So I'm going to introduce like 2 methods here. If you find other methods, that's fine. But I think probably most of you guys will just take these 2 methods, what I introduced today. So you can see there's a map of the toolbox. This is like a huge amount of information. And actually we're going to use is pretty much just that very simple one, the transfer function, that's it. All the other complicated stuff we don't need to use. And this is a page 53 of that document, that basically how to create a transfer function. So you can find all those details, either just go to the MATLAB and type in, say, just help TF, so that's the transfer function. And you got help and information, but if you don't even know the name of the function, then you have to kind of a little bit look at this document and find out what commands you wanted to use. All right, let's get back to here. This is just quickly mentioning C2D. This is a command that's very relevant to what we're going to talk in week 10. So I'm not going to talk details here. So next week, probably I'll do another separate kind of a lecture just on this topic. All right, let's jump into the example. Let's jump into example. So this is example I take partially from this University of Michigan webpage. So it's the cruise control. This example, I made some changes in the later stage. So I'll just take that as most kind of simple example I can think of to explain the situation. How do you actually do a project? So the project first step is you have to identify an object, what kind of control task you want to do. And then you build up a mathematical model for that. So the mathematical model we are talking about mostly is the differential equations. It's the relationship between the input and output, normally with a certain kind of differential kind of relationship. It's not direct, like input direct to output, because we're talking about a dynamic system. A dynamic system means it has certain kind of way of storing energy. So the input doesn't go to the output directly. Normally it's take a bit kind of wire for the input to be reflected to the output. And that's our kind of mathematical relationship. So in this case, you have the input is the power, okay? The power U, that's the power from the engine, okay? The output is the speed of the car, okay? It's x dot, that's the velocity of the car. Sometimes can be the position of the car, depends on what you do. Say, if I wanted to just drive the car to maintain a certain speed, say 100 kilometer per hour. So the speed is our goal of control. And sometimes you have, if I want to say there's a red light in the front, I want to stop right at that in front of that red light. Then the position is your control target. So different times the control goal is different. And in this system, there's a power or the engine that drives the car forward. There's a force that trying to slow the car down, and this force is proportional to the speed of the car. So the faster the car moves, the larger the kind of drag force or the friction force, or the initial the force from the kind of the air dynamics is going to slow the car down. So we just simplify to that. It's the actual case is more complicated. But say this is our physical model. You've got the first step down. Okay, that's our physical model. You got all the force and also the mass is of the car is m. So we've got all we need here. And from the physics, we can get an equation. So the basically the mv, so not mv, this is ma, the force, the acceleration. This is the acceleration of the car, equal to the u, that's the engine power, minus the bv, that's the friction or the force that drag the car. So if you just move this on the other side, so that's the balance of the force. Okay, so v dot is basically a, so that's the ma. Okay, so very simple first order model. And if we remember, our output is v. V is what we want to control. Our input is u. So from that, we can get a transfer function. The output is v, input is u. Okay, so that's our kind of plant. We call it a plant, is our control target. It's very simple first order transfer function. So far, any problem? No? Everybody understand what I'm talking? Yes or no?
Yeah, it's all good.
Yeah, all good. So this is our first order transfer function. The input is the engine energy, or if we got more details, I put in here. The first order system, I just write it in a different way. This way, and compared to the one beforehand, 1 over MSB, there's no difference, okay? This one is 1 over MSB, and over here, I just make it like that. So the same first order system, but this method, writing this down, is I make sure the gain of this, no matter what is the frequency, the low frequency gain of this is always 1. So it's kind of unit gain. If you write like that, you end up with different frequency have a slightly change of the gain, which is identical, but sometimes the later method is simpler, but doesn't matter. So
I have a question.
Yeah, sure.
So can you scroll up a little bit? How did you get that 1 over ms plus b? Like how,
Okay.
if we are going to do our projects,
Yeah.
how are we going to determine the PS?
So that's this thing. Yeah, that's coming from there. What we do is we do Laplace transform of this thing. Okay, so anything with a dot means you have this is a m, doesn't change. V dot means it's going to be get a s. This is a vs. Yes. Plus b. V is basically vs. So this is basically a Laplace transform. U is becomes
right. Okay.
us. Then you divide vs with us and to get all the other things to the other side. Makes sense?
Right. That's right. Thanks.
Yeah. Okay. So that's Laplace transform. Okay. So we're doing this in continuous time domain. So after that, a more intuitive way to think about that question is this is our transfer function. That's our plant. this is the speed of the car. Like I said, this is the power, but sometimes power is not that easy to understand. So what exactly is that? So if we imagine this is a car we're having, so that's the theta of kind of the pedal. You step on the pedal. The more you step in, the theta will change. The more kind of larger the theta, the car will accelerate more, right? So kind of you can step to the bottom and make a very large theta, and the speed will change fast. But however, something we have to remember there is this thing has a certain limit. Right? You can't really go too much because you can only step that kind of put down your foot completely. That's the limitation of the power of the car. Right? So you have certain limiting here. And this is something I'm going to mention a bit later. This is important when we design controller. Very often we ignore this thing. We forget about this limitation of our power. We just say a big controller like that and it's going to achieve our goal. However, we forget because our controller actually have certain limitations. You can't really do that with the idea kind of controller. I'm going to mention that a bit later. So let's get back to this thing. So this is our plant. So the next step is we have to define what's the goal of our control. What do we want this plant to behave? Okay, so this is quite arbitrary kind of standards I put in here. Say I want to rise time to less than 5 seconds. It means like if I wanted to speed to be 100 kilometers per second, the car needs to get there like within 5 seconds, right? So, or not exactly there, get to 90% of what we want it to be within 5 seconds. So it's kind of a normal car, right? You want to accelerate to say certain speed within like 5 seconds, reasonably fast car. And you want to overshoot to be less than 10%. So it means like if I set to 100 kilometer per hour, it won't go crazy, then slow down. And need a steady state error to be less than 2%. So if I set to be 100, it won't just get to like 80 and stop. The last one is what I add up. The motor power needs to be less than a certain limit. So this is the engine capacity, or this is our pedal. You can only step that much. Okay, you can't really accelerate as whatever you wish because the car is has certain limitations. Okay, so with this in mind, how do we design a controller to achieve all this? So you can see all these criteria, all these specification. This is all the time domain. Also, you can specify a certain frequency domain criteria. So these are some background knowledge you have to prepare over here. So you should go back if you forget about all these details. You have to go back and learn this basic information. So there's two different set of design or analysis kind of criteria. One is time domain we just mentioned. Normally we include a steady state area, rise time, overshoot, setting time. It's all marked on this figure. You have to go back and read the book and what all these means. And also important thing is what are these things related to our controller? Like if I change the controller somehow, how the behavior is going to change. Okay, so those things are kind of try and error. There's a rule of thumb that you can get, but those things that are basic things you have to get from some other source. Or you can just check the MATLAB. So all this stuff is in MATLAB. I think I marked it over here. Time domain answers, that's in here. You can get to MATLAB to help you. In time domain, the easiest way we can get a controller is using a PID controller to suit our time domain requirements. It's not the only method, but it's one of the kind of most common and easy to implement method. Okay, so that's the time domain. This, oh, why this thing move with me? something with that box. Doesn't matter. So the second important thing, when we do this system analysis or system design criteria is frequency analysis. And there's a root locus and the bow diagram. I will just recommend the bow diagram. Don't go to the root locus kind of method. So bow diagram, you have to be able to understand all these meanings. What's the phase margin? What's the gain margin? Gain crossover, bandwidth, and also zero frequency magnitude. So I'll just quickly go through. So phase margin is when you have a gain equal to 0, and at that frequency you go down. See how much that phase is more than negative 180. So in this case, this is about negative like 100. So you have like around 70 degrees of phase margin. And the crossover, gain crossover, that's this frequency, that's this omega crossover. Okay, so in this case, it's about 1 radian per second. So when we draw this bow diagram, the horizontal axis is our omega. And what we use here is S equal to J omega. So you can consider this horizontal axis is basically when the S is going from 0 to infinity. And vertical axis, one is the magnitude of the transfer function, the other is the phase change of the transfer function. And the most common thing we use to control our system or to tell if the system is good or bad is look at the phase margin. Okay? And the controller that very easy to be used to achieve certain kind of frequency domain requirements is lead lag compensator. Right? It's not the only one, but that's the kind of most common one, and very easy for you to just find relevant materials around this lead lag compensator to be able to achieve certain phase margin. Say if our original system only have 10 degrees of phase margin, you can easily create a lead or lag compensator to expand the phase margin without too much kind of disruption of other indicators. Right, so that's a quick background. And you probably going to choose either method, either go from frequency domain and use a lead lag compensator, or you go to time domain, get a PID controller. Either way, or you can mix this together, but this is kind of the basic continuous time domain methods I want you to adopt for the controller design. All right, so let's get back to our question. Our question is why this box is kind of moving with me. Where are we? We're here. So we first look at the time domain analysis. So that's kind of a step response over here. So before we do any controller, we just say, let's take the simplest one. I just have this is our controller. That's a structure. So let's just do a simple one. So instead of this PID, that's too complicated. Let's just take a KP. I just put a gain there. I can make the gain just equal to 1 and see what the system responds by itself without any control. So that's what I'm doing here. So I've got a MATLAB code over here. And that's the time step response. So I'll probably just do a simulation with the MATLAB. Just run through so you know I'm not just cheating with the numbers. Probably change the parameter a little bit here. So I think that's the first one. So that's the first bit. So the way to run MATLAB code, if you're not familiar, I normally wanted to drag this code. The code when you install the MATLAB, this is inside that window. I normally wanted to drag this out. So put two windows side by side. And this is your editor. You don't just type the code in the MATLAB window. You create M file and save your code over there. And I wanted to use this double comments. this is define a section, then you can just run the section to run everything highlighted in yellow here. Right? That's how you control. And I get another double comment. This is another session. So it's very easy. Just highlight this session and run the session. It will run the coding here. So in this case, I just want to run up to here. So get a double comment over here. So if I highlight this yellow, I have to save this. Command S, save this, and I just run section, which will just run this yellow code. Okay, so this makes your debug much easier. So what I did here is I designed the control transfer function. So S equal to TFS. This is basically just convert this S into the Laplace kind of symbol rather than alphabet kind of character S. So now S is become our kind of transfer function S. I can use it directly. I define the mass and the damping constant. Say reference here, I use 10 because if we use the kilogram and if the damping is like a Newton meter per kilogram, this unit is meter per second. So I say just 10 meter per second, which is like 36 kilometer per hour. It's very slow kind of target. Okay, I just say 10 is our reference. This is our transfer function. So this is coming from the, if we see, this is coming from here. Okay, so 1 over ms plus b. That's exactly this one. That's our transfer function. I just get a kp as our transfer function, as our controller. Very simple controller with p only. So you can construct a PID controller, say PID KP. I use this because later on I'm going to have PI and PD in there, just easier to construct it. But you can say this one C equal to PID KP basically is C equal to KP. You can just multiply the KP in there. And I use another function in MATLAB. This is called a feedback. So this one just basically build a complete feedback loop, CP1. So if you look at this diagram, so this feedback basically close this loop, okay, from the input to the output. Output is a V, input reference is our reference speed. So here, every single kind of this variable become very clear, and the goal is very clear. So our reference is what we want to do. So we want to set the speed to be 10 meters per minute. And our outcome is the speed of the car, which we wanted that to follow the reference. Want the speed to be 10 meters per second, with like within 5 seconds, and also don't go to 11 or less than 11. The maximum it can go is less than 11. And finally, it should be around 10, not by too much. Okay, shouldn't be like less than like 9.98. Okay, and also the motor power. So in this case, motor power is not here, right? You can't really see what is U here. But then we can do a simulate and read the signal over here. We can do that a bit later. So far, let's just look at what it is for now. Okay, go back to the figure 1. That's our step response. So our reference is 10. So obviously, it takes 20 seconds and not even getting to 10. And you can see this dotted line here. That's where this signal is going to converge. So eventually, it converges to like 7 or not even 7, 6 point something. You can right-click the figure and to see those indicators. Say if I say steady state, right, then you can see the final value is 6.67, and you can see rise time. So those indicators can be plotted on the figure, which gives you clear exact number. So rise time is 14.6 seconds, which all these values are kind of much worse than what we want. Okay, so first thing we need to do, like, to think about this is let's look at the steady state arrow first. Okay, so we wanted to get from 0 to 10. At the moment, it's only getting to 6-ish. Okay, so let's try something, right? We don't know what to try. Let's try something. The first thing we try is, let's say, I still wanted to just use a very simple controller, just like KP, but I make the KP very large. From 100, we increase to 5,000, okay? 50 times larger. And we'll just see what's that going to be. So I just run this part. Right? If you had a look, this is quite good, right? This is very good. If you compare to what we want to achieve, is steady state less than 2%. So this is very close to 10. You can say that's pretty much okay. Overshoot less than 10%. There's zero overshoot in our case. Okay? The reason for that is because our system here is a first order system. First order system never going to have any overshoot. We can explain that from the bow diagram a bit later. It's only when you have second order or high order system, then you get an overshoot. And rise time less than 5 seconds. You can see this is like half second or 1 second. It gets to what we want. So this is perfect, right? So we can say controller design is finished. All right, we just get a KP controller here, make the KP very large, and all our criteria is satisfied. Okay, however, I'm going to mention that's not the case a bit later. Okay, so let's see. I only wanted to have a look at the bow diagram. That helps us to explain why the I'll just plot the bow diagram and why the system never going to have an overshoot. Where's the figure? Okay, so this is the bow diagram of the system. I'll just do a grid. So just mark all the things over here. So this is the bow diagram of the system. Like we mentioned, for the system to be stable or unstable, we look at the phase margin, right? So in this case, we look at when this thing crosses 0. So it's kind of on the right hand, a little bit over here. It didn't plot the whole range suitably. But if you look at the phase here, the smallest phase that gets to is negative 90 degrees. And remember, our phase margin is when this point minus negative 180. So no matter what's the case, we will have more than 90 degrees of phase margin here. That's why we don't have any potential to go to unstable. The system is always stable and always have no overshoot, right? Because it's the only first order system. The worst case the phase can go to with the first order system is goes to negative 90 degrees. Right? So that's the first thing we mentioned. So this seems to be a good controller. And here, there's other criteria we haven't seen is the motor power has to be limited. Okay, we haven't checked that. So we have to check this motor power, the U here. Okay, so how we do that? In this kind of MATLAB code situation, it's a little bit harder to do. You can still plot that U somehow, but I'm going to use another method. So like I said, there's many different ways to address the same problem in MATLAB. So let's look at another method. How do we see the control signal? So I'm going to use the MATLAB Simulink method. So I already built a model in Simulink. If I turn this. So this is a Simulink. Well, I don't have a keyboard here, so it's a bit. I don't have a mouse here, so it's a bit problematic for me. So this is the transfer function. Okay, so 1 over ms plus b. If we look at this, that's basically that. Okay, I can change this thing by, this is basically m b. Okay, that's the same thing, because in here m is 1000, b is 50. If you drag this bigger, then it shows up. The way we define this is basically we set up the numerator coefficient and denominator coefficient in here. Okay? In here, I use the two variable m and b. So to be able to run this, you must have run this code first. You have to define m and b with a value. Otherwise, it will like this. I can highlight it because some of the variable here is not defined. So this is a PID controller. So because I put a KP and KI here, KI is not defined. I haven't run up to that code yet. So I just make that 0. Then it's okay, because I run this part of the code. I got a KP. I haven't got a KI. So how do you generate this thing? So this is a block. You can go from the library. This is a transfer function. Let me see, how do we get this transfer function? So probably just go to the continuous. So these are the common things you're going to use. Like transfer functions here. You just drag it into your Simulink, double click, and you define your denominator and numerator. Okay, then you just collect the wires. Okay, so that's how I got these things. How I got this. Then the PID is you can get also get from here. There's particular PID thing in here. So you just say PID. Yeah. So you just drag it over here, then double click, give you all the KP, KI, KD. So in this case, I got this like KP is KP. Yeah. So that's what I put in here. I got a KP. I didn't have choose here is only a PI, or I can choose a P because I don't have I or D yet. Okay? And then get a KP is the value which will take from this one, because I leave it as a variable. So, and I build a feedback. Now I can put different scope to see the kind of signal. Right? So the scope is coming from the sync. So that's the scope. Just drag it over here. Then you can right click to change all these parameters. You can make it like 2 input. So this will display the both signal. And you can get another scope just to look at this signal. This is the U. Okay, remember the previous design? We had a look at the output. Let's just run this. Just run this. So we should have this output somewhere there. I got a lot of errors here because I've got other things that linked to this. This part, this other part, I've got other variables that are not defined. So I have to run this whole code just so those coefficient actually get some values in there, so they don't go kind of undefined or give me errors. But after that, should be fine. So after that, I run this first bit again to override all the changes. So this should run for now. Yeah, so I just look at this scope. So the yellow one is our step response. So it goes from 0 to 10. And the controller, this PS, at the moment it's KP is 100. It's very slow. And the output is in this blue one. So that's exactly the same as step response initially we have. Then we change this KP to be bigger, right? That's what we do. This will make our KP become 5,000. If I run this again, so this is the step response. So this looks good, right? This satisfies all our needs. until we look at what's the control signal. So if you look at the control signal, what this controller asks the driver to do is you have to step down with 5 multiplied with it's 50,000. I'm not sure the unit here, say 50,000 kilowatt or watt, say even watt. It's 50 kilowatt. Yeah, so to drive the car, then it's slow down to achieve that performance. If we compare the previously KP is only 100, the initial power with a very slow controller, is initial controller, the control signal we have is 1000. So it's kind of, we put the gain here by 50 times. This actually, what it does is ask the controller to output 50 times more power to achieve our goal. Now you realize our controller doesn't have that, our motor don't have that power. Right? So if we have our limitation here, our power is only 10 kilowatt. You ask me to output the 50 kilowatt, I can't do it. So even through the simulation looks perfect, but there's not that enough power for the system actually to achieve it. So when you design a controller, this is something very often you are easily kind of forget. You come up with a crazy controller. The numbers goes extremely large, and you have to go back and check what does this number mean, this KP mean, and what this make the signal change, like control signal change. If it's kind of unreasonably valued, then you have to go back and try to do something else. So what else do we do is we, this is actually goes over the limit. We can only have 10,000 and this is 50,000. So we have to do something different. We cannot rely on just a large game to achieve our goal. So instead of just a KP, we get a PI control. Okay, we have an integrator that help us to achieve those steady state error. So it's a bit kind of, we don't have that enough time. So some of this I will just skip through the these slides. So let's say we don't make the game super large. We say the game is 800, okay? 8 times of original, but I put a KI component in there. So in that case, say I have a game of 800, I have a KI is equal to 40. Let's see what performance this one's going to do. Right, so at the moment, I'm just doing some try and error. Right? The controller toolbox actually gets something called a PID tune, which you can use, kind of provide certain standard, give you a controller automatically. The software is going to help you to choose this parameter. What you need to do is specify those control criteria. So that's kind of automatic tuning tools in MATLAB. There's a couple of them. You can choose to use those tools as well. But at the moment, I'm just trying to explain by manually kind of adjust. So this one, we have KP is 800 and KI equal to 40. You can see rise time 5 seconds. Well, 5 seconds is pretty much there. Overshoot, that's always happy. So this criteria, whatever you do, if you don't put too many other kind of posts in the system, it's going to be always happy. So that's okay. Steady state error, that's okay. Well, that's actually 0. So even the previous case, we go to the previous case, you have a large KP. In this case, you still have a small steady state error. However, once you get a KI in there, you can see the steady state error goes to 0. And the reason for that is I put some information over here. The reason for that is the type of the system. So it's coming from here. The type of the system means how many poles you have at 0. So if you have poles at 0, so if you have an integer, there's power n over there. So if n equal to 0, you mean it's a type 0 system. If this n is equal to 1, you got a type 1 system. N equal to 2 is type 2 system. The steady state error is depending on how many poles you have at origin. Right? So that's what PI controllers do. PI is P, KP plus KI over S. And this is basically S over KPS plus KI. So PI control actually added a S. So we turn our system from type 0 to type 1. So that can remove the steady state error. So that's additional information you have to go through and maybe read other books to get fully understand. So that's what's the benefit of the KI. It actually removes the steady state error. As long as you got this this I component, the steady state error of step response is going to be 0, just faster or slower. So in this case, actually, also it satisfies all these standards. And if we look at the motor power, okay, I'm not going to run the Simulink again, but this is the output of at motor power in this thing. Okay, that's our control signal. If we look at that again, in this case, it only goes to 8,000. So this motor power actually, the proportion to the KP. All right. So in this case, we don't have to drive our car that crazy or to the limit or over the limit. We only need to get, say, 8 kilowatt kind of power, and also can achieve our goal. It's not as fast or as crazy like this one. It's not going to step up and like that, because your car won't be able to do that anyway. And it gets kind of a more slower, nicer, but approach to the goal as well. So another thing about control design is you don't have one perfect controller for everything. It's all about trade-off. You can get certain controller good at one of these criteria, but bad in other criteria. There's no one controller going to make perfect for all these criteria. So it's a trade-off between these criteria. Right? So there's another thing you have to consider is everybody will eventually, even the control object is the same, everybody is eventually give different controller design. So from Wikipedia, and you can get from some other resources, there's a systematic way to tune the KP, KI, KD. Right? There's many different methods to keep the proportion of KP, KI, KD to a certain extent. And you just pick one of the methods, do the try and error. This will give you some certain controller that satisfy our requirement. Is that so far all clear? Does that make sense to you guys? Anybody? Just
yes.
Yeah, that makes sense. So this is how you design a continuous time controller for your plant. Or first step is how do you make a model for your plant, and then you have the time domain specification and how to get a PID control manually by trying different things, trying the KP, KI, and you can try different values and see how the response goes and see if the criteria is met or not. Also, you can do that in Simulink, build a block, and with Simulink, you can see the signal from everywhere, which give you a little bit more freedom, but these two are basically manual method. You manually try these things. So like I mentioned, there's actually another tool called let me find that. There's another tool called a PID tune. Right? So you can find this information from the big document, or I copy and paste a few things over here. So basically this thing is like a toolbox in the control system design, which you provide a certain criteria and it automatically chooses PID parameter for you. It's called a PID tune. You can use that. However, I still think do it manually give you more intuitive understanding of how each parameter change and how the impact to the time domain response. Okay, so still you can do this too, but it's just alternative. It doesn't make kind of make things easier. Okay, when you use the tool without understanding how those coefficient works, then it just become a mystery for you. So it doesn't really help you. But I put this in here anyhow because it's kind of more smart kind of way to address this. Okay, so that's the time domain. Another part of this is you can look at this system and set up the criteria in frequency domain. I can say I want a system to have a certain rising time and also have some phase margin. So phase margin is one of the things that we normally specify to make sure systems are stable. The larger the phase margin, the more stable the system is. So normally we will specify what kind of rising time and what's the phase margin we want. So if you have that phase margin, doing PID control is fine because after the PID control, you can still plot the bow diagram over here. You can still check the phase margin. That's fine. You can do that. However, this is not that simple relationship. You can't just easily get a relationship by changing the KP, KI, or KD to know like what kind of phase margin you are getting. It's more of like you randomly try some parameter and see that phase margin is good or not. Another method we call lag lead compensator. So this basically is the same compensator, just with different parameters. This compensator is actually very intuitive and easy to kind of be used if our goal is just say look at the phase margin. So I use another example that's in here because I don't use the previous one because that's a first order system model. Like I said, it's going to always have more than 90 degrees of phase margin. So you specify phase margin over here doesn't really make sense because it's a stable system by itself. So here I create another model. It's a second order model. So it's just this one. Transfer function is that. I'm trying to see what looks like with a little bit of KP, KI, KD. I'll put just random things there. See what looks like. Okay, so I plot the step response and the bow diagram. You can see this time you get overshoot. The second order system will give you overshoot. And then you kind of have a little bit waving, then goes stable. Okay, so this time the reference is 1, so this will expect to go to 1 eventually. And I plot the bow diagram, and this bow diagram give you a bit more things to go because you have a second order system. So at the bottom, you sorry. How do I do this? I need to see this window and this window. Give me a second. Yeah, so that's the system. So you can see we have a second order here, which means the phase diagram will go from 0 to -180. If you only have the first order at the bottom, there's one pole at the bottom, this only goes from 0 to -90. So this time it goes to -180, but in this kind of shape. Right? So we can look at the phase margin by checking the bow diagram. So that's a 0 crossover frequency. You go down here. The difference between there to -180 is your phase margin. Alternatively, you can just use the command. You can use this command to plot the phase margin. If I just do that from the window, this gives you gain margin, phase margin, the frequency for the gain margin, and the frequency crossover frequency for the phase margin. Okay, so phase margin is like 30 degrees. If you check the figure, this is about right, 30 degrees. Then you can change this PID parameter to muck around and get the phase margin. Okay, that's the thing to go. However, like I said, the relationship between this KP, KI, KD and how this phase change is not obvious. So sometimes like you got this kind of changing around, but the phase margin doesn't change as you want. So the other method to design this is through a lag compensator. So lead lag is 2 kind of type of the same compensator. You either use one of them. Okay. Another thing to be very careful here, when I draw the step response, it's for the feedback loop. It's for the closed loop. Okay, that's one thing you have to be careful. When I do the step response, time response, it's for the complete closed loop. But when I do the bow diagram, this is open loop, right? I didn't do the bow diagram for the T. I do the bow diagram for the controller multiplied with the plum. We always look at the bow diagram, phase margin, gain margin, and those things for the open loop. We don't look at that for the closed loop. Okay, just make sure you understand that. And reason is quite complicated. You can check the textbook and can Google, find why is that's the case. We always use open loop bow diagram to indicate our system. Okay, just don't get confused in here. Another compensator is called lead lag compensator. So let me see. Only have like 4 minutes. So the compensator is something like this. If I write it down, the compensator, this is a lag compensator, is equal to S over omega 0 plus 1 S over omega po plus 1. So basically you have like two first order, both on the top and the bottom. So if this omega S is less than the omega P, so you will have a bow diagram something, let me see, less than this goes to 0 earlier. So the system will be like this. That's your gain. This is your magnitude. And your phase will be look like, this is your phase will be look like it goes down, then goes up. Okay, this goes to negative 90 degrees. Okay, so this is basically at certain bandwidths. So it does impact at certain bandwidths. It's going to change the phase margin. So this is the kind of the area you got less phase margin or more phase margin. If this omega 0 and omega p, you swap the value, it becomes offset. So the top can be this one, the bottom becomes this one. Okay, so like this one is perfect, right? If our system only have 35, where's our thing? Where's our bow diagram? Let me see. See in here, our system only have 30 degrees bow phase margin. If we want this phase margin to be bigger, what we do is we have a bump over here, right? We overlap a bump over here, like this one, and get this kind of controller on the top. So the gain over there doesn't change too much, but the phase will have kind of a lift, a phase lift over that particular frequency. And this is what happened over here. Get a little bit lift over there by choosing omega 0 and omega 1. So omega 0 is when I start the lift. Omega 1 is when I finish the lift. So it's kind of a band. And in this case, we are looking at something around 100 hertz, right? We want to start lower than 100 and finish about higher than 100. So it's still a try and error case, but you can say what I pick here is that you can pick from 10 radian per second, I will start lifting, and go to 100, I want to put it downwards. So finish the lifting. Okay, so for a certain frequency, you can increase your phase margin by doing this lag compensator. Because of the time, so I'll provide this code and the slides in PowerPoint. If you haven't come to this session, and if you don't fully understand, hopefully this recording is going to be good. I can't attach the whole video from on the Moodle because the size is just too big. So I have to attach on Google. I'll put a link over there. All right, so that's what I'm to mention here. So I'm not saying you have to exactly follow what I'm doing here for your design. This is just one way of doing it. Okay, so in week 10, when we design a system, so this is going to be the steps for your project as well. What I just mentioned is basically the first two steps. Design a system in continuous time and check the behavior. That's what we did so far. Because this is content, I think, is the previous knowledge, but most of you probably forget what to do. So I just give you a little bit of information. So help you to find the help you need by yourself. Okay, so that's all we have time. Do you have any questions? I can stay for the questions. Otherwise, you guys can join the tutorial sessions and do the tutorial and submit a question. About that, so I put Friday 5 p.m. as the deadline for the tutorial. So today you can still ask questions. Then you can submit on Moodle by tomorrow. Okay. So today I'm not going to put the solution on, but by the weekend I'll put the solution up. And also today you can ask a question about the midterm exam. The tutor will show the solution to you guys. We probably don't put the solution on Moodle, but he can share the screen and show you how kind of to solve each one of the question. All right, any questions? Is this one helpful? I'm not sure because I'm go very fast. Yeah, because that's kind of a lot of information and I can't cover everything. So I just pretty much give you a clue and you need to go back and find things kind of by yourself. Everybody gets very different background. Yeah, that's what I'm trying to achieve here.
Yeah, well, the only thing is that because you've covered this much and we need to take extra time. I mean, like more than extra time to, to understand what everything you just mentioned. It takes a lot of time to do that. So what I'm thinking is that so for the next session, if you can give us the resources that you're going to share in the lecture, like in the lecture time earlier, so that we can do some study on it first, and then we can understand you better during the lecture, so that we have questions to ask.
Okay.
Otherwise, this is like because most of the stuff that we need to do research on to make sure that we understand it, so that we can ask questions. Like, I mean, for right now, I do have a lot of questions, but I think most of them can be solved by conducting more research.
Yeah. Okay. So the reason I don't have this beforehand is because I'm recording it on like real time, so I can't really have anything to share with you. That's why I put the lecture slides beforehand. This is additional information that pretty much if you guys are doing very good in the control theory before, this should be something you already know. So I'm just trying to bring up some memories here, not really be able to cover one semester of content in 1 hour. But just give you a refresh memory. You don't have to go back and read everything. These are the relevant information you have to go back and review. So that's kind of where I come from. But next Monday and next Wednesday, 8:30 to 9:30, I'm available for questions. So if you have any question, you can ask me next week about this week's content.
That's right. But like for most of the students, I'm not too sure. For some of the students, they may just come to the master degree from bachelor degree straight away. But for some of us, like me, I have been working in like other fields for many years, and then I'm coming back for engineering. So some of the knowledge is a little bit vague for some of us, at least for some of us. So I think there's I'm not sure how to to compensate for that, but just based on your experience, like what sort of ways that you can to minimize the our disadvantage, to just to minimize our disadvantage.
Well, this is exactly why I'm putting this lecture in. Otherwise, I won't do this because I'm assuming you all understand this. So like I said, there's many different ways to do control design. So I put these examples of steps. If you're not kind of familiar with all the methods, you can just take what I teach you in this hour, the time domain and the frequency domain. So the bow diagram, step response, that's the most kind of fundamental tools. You must go back and review these information to be able to kind of make sense to yourself. There's other methods like a Nyquist diagram. There's other stuff, tons of other stuff that you can just ignore. You don't need to know those things. I understand this subject has prerequisite for the basic control theory, and because this subject is normally in other universities called a modern control theory. It's very mathematically intensive and it's hard to understand. So really, it's going to be a challenging subject. And also my experience previously is if I just do the lectures and you do the questions, in most cases, you can learn how to do the question, but you don't know why are you doing that, and you have no clue like why I'm spending so much time solving these very challenging question and without knowing really what's going on. So that's why I put this project in there. So you have to identify a real problem and going through the steps to address a real problem. So each step, there will be multiple ways of doing that. So I'm not kind of asking you to try all the methods. You just follow like one method I just introduce them. Then you get a complete case with kind of one way of doing that. So at least from that point, you know, like what I learned actually can be applied somewhere. And next time when you have an actual problem, you can kind of link to what we are learning in the subject.
Yeah, I got that part. Yeah.
Yeah. Okay. So we are a bit over time here. If you have more questions, please come to my consulting time. That's Monday morning, and also 8:30 to 9:30 before this lecture time. I'm available every week from now until week 12. And week 13, we'll do some kind of a presentation for the project. Okay. All right. Thank you for coming. Now you can go to the tutorial session if you're in the morning part and ask the tutor about the detailed kind of more mathematical questions. All right.
Thank you.
All right. See you guys.
Thanks. Bye.